Hello, it's Ryan. Today we're going to go over Coulomb's law in a little more detail and do some examples. Coulomb's law is pertaining to electric force, which I mentioned in lecture was an action at a distance force, meaning it reaches through space and time and seems to cause forces on charged bodies due to other charged bodies without seemingly any physical interaction. So it reaches through time and space and acts on things at a distance. Hence, action at a distance forces. Before we move on and do a mathematical example, we kind of ran out of time in our lecture, but I'd like to make a little blurb about the fundamental forces. And actually, there are 4 fundamental forces. And the way I'm going to do this is on as a plot, where we're going to plot the type of force, or each of our forces, with respect to distance and strength. So strength is not necessarily the most perfect word. Maybe we could say magnitude or something, but strength makes sense, so we're going to keep it. The first 2 I'm going to add in here are really close quarters forces. So the way I'm going to do this is like so. We'll have a bar that goes up like that. And I put 2 little dashes in there. These 2 little dashes here imply that this bar would actually be way up higher in our scale. So this is by far the strongest force. It's about 10 to the negative 18 meter. And that is the strong force, or the strong interaction. Nuclear interaction. So this happens in the nuclei of atoms. The next force we'll put here. It's like so. This one is the weak interaction. I'm not going to write there. Usually the weak interaction, this is the phenomenon that we usually describe, is how we describe how we would discover dark matter. That's one way to think of it. Anyway, 10 to the negative 15 meters is where this is the strongest, or where it interacts. So these are both atomic interactions. The other 2 fundamental forces occur on a more macroscopic level as well. The first will be the force due to gravity. We talked extensively about the force due to gravity in Physics 1. It was an inverse square. The force due to gravity. And now, in this class, we're adding a couple other forces that really are inextricably connected, like so. This is the electromagnetic force. And I've drawn it, as you can see, the same shape as gravitational force, but it is always stronger than the gravitational force. And believe it or not, that's a good thing. Gravity is kind of always acting on you, keeping you stuck to the surface of our planet. But if gravity had its way, you would be as close to the center of the Earth as it could get you. And so that means all your atoms and molecules that you're made of would be smashed to the surface of the Earth. So we would kind of be like pancake puddles. But luckily, our atoms interact via these other stronger forces. And so we get to keep our shape. The electric force that keeps like charges repelling each other keep our atoms and molecules in the shape that we end up maintaining throughout our life, instead of just becoming a puddle person. So it's fortunate that the electromagnetic force is in fact stronger than the gravitational force. What we're trying to do in physics, just to add to our little blurb, is we're trying to unify all these forces. We want to unify all four forces into a single force, which we usually call supergravity. Now there's a lot we could talk about with this. We could do a whole class called cosmology on this. But in general, that's one of the major goals in the study of physics, is to unify these forces. And we've started to. Actually, what we've done is we have unified the electromagnetic force and the weak interaction. So now we call it the electroweak force, or electroweak interaction. And so what that means is, right now in physics, we've actually only got 3 fundamental forces. And we're trying to come up with a way to unify all of these to only have a single fundamental force that we like to call supergravity. Anyway, just a little bit on forces, these wonderful action at a distance forces, and that will be the end of our blurb. And so we can move right into an example from here. So this is our first example of using Coulomb's law. In this example, we have 2 point charges that are located 5 micrometers apart. If you don't remember, micro is 10 to the negative 6. If the first charge is negative 10 millicoulombs and the second charge is 13 millicoulombs, so innately that's positive because it doesn't have a negative sign, determine the electric force on each of the charged particles. So we're going to be looking for 2 vector answers because force is a vector. And we're going to go through each step of our problem-solving method to do this. We're going to start by drawing a picture, of course. And our picture doesn't have to be complicated or anything. We're going to just draw our 2 point charges, Q1 and Q2. There they are. And we're going to show that they are some distance apart, r. And we are, I guess that's really it. Normally we would do free body diagrams if we're analyzing forces, but because we're ignoring all other forces on these things, like it says in the problem, we're just going to go ahead and in our picture put the electric forces that these will experience. So what I want to show first is that this is actually a negative charge and this is a positive charge that was given. And so we know that these will create attractive forces on one another. And so that means the force on Q1 due to Q2 will be toward Q2. It will be attracted to Q2. And so I'm going to show that like so. There will be an electric force, Fe, on Q1. And it will be toward Q2 because it's attracted to a positive charge. And I'm also going to show that there's an attractive electric force on Q2 due to Q1. And we know that those are going to be equal and opposite. Well, of course, because of Newton's third law. But if we were to plug into the equation, we'd also see that because we'd plug in the same charges and the same distance, then we'd of course get the same numeric value. But in our picture, we can also see that these are going in opposite directions. So something I'm going to show on here is that we're just going to make this direction our positive x direction, just to have some positive and negative values if we need them. Once we have a nice picture like this, we can put our knowns and unknowns. And so we'll have the radius, which was 5 micrometers. Sometimes people call those microns. 5 times 10 to the negative 6 meters. we know Q1 was negative 10 times 10 to the negative 3 coulombs. Q2 was 13 times 10 to the negative 3 coulombs. We also know from previous notes that Coulomb's constant K is 8.99 times 10 to the 9 Newton meters squared per Coulomb squared. We'll need that when we use Coulomb's law. And I know that we're looking for Fe1 and Fe2, the electric force on Q1 and the electric force on Q2. But we do know that the magnitude of these forces, the amount, must be equal because they are equal and opposite forces. So those are all knowns and unknowns. So we're going to go ahead and try to solve for the electric force experienced or that will be on each of these particles. So we're going to use Coulomb's law. Coulomb's law was Fe equals K Q1 Q2 over R squared in whatever direction it is. It's a radial force. We're going to drop vector notation because it's one-dimensional. So we can see clearly these are going to be in the x direction, so in the end we can just input that. So we have the electric force on Q1 is equal to, and we don't have any algebra to do, we can just go ahead and substitute the values. So the 8.99 times 10 to the 9, Q1 was the 10 times 10 to the negative 3 coulombs. Q2 was the 13 times 10 to the negative 3 coulombs, all divided by the 5 times 10 to the negative 6 meters. Now something I'm going to note here, I normally probably wouldn't, but I'm going to note I'm ignoring negative signs. And another really good note might be, just to have it, we will ignore negatives on all vector calculations. And input negatives when the vector is in the negative direction. This is fairly unique. Oops. This is fairly unique because normally we would never ignore a negative sign in our equation. But from our picture, it's quite obvious to see. Fe1 will be positive because we chose right to be positive. Fe2 will be negative because we chose right to be positive. Now, if we were to actually substitute the negative value in for Fe1 or Fe2, Q1 is always negative. So both of those calculations will actually give us a negative value. That's why I'm going to ignore it, and I'm just going to input the negative sign when I write the electric force on Q2 because it's in the negative direction. So it's kind of a strange request, but I think it'll help in the end if we allow the picture to put in our negative signs anytime we work with vectors in this class. So you'll see there will be other circumstances where this holds, for example, electric field calculations. But we're not there yet. If you were to punch this into the calculator, you could show that the electric force on 1 is equal to 4.67 times 10 to the 16 newtons. It's huge. And we're going to input a direction here. I like to use unit vectors. The unit vector for x direction is I hat. So that would be fine. Another way you could write this, just since this is our first real vector example, we could write 4.67 times 10 to the 16 newtons, and we could say horizontally. That would be fine. Or you could say at 0 degrees, but I personally like the unit vectors, and so that's what I usually use. Because these are equal and opposite forces, we don't have to go through and recalculate all this. We can just write that Fe2 is negative of Fe1, which was 4.67 times 10 to the 16 newtons in the x direction. So our negative sign helps with the direction. And now we have the solution for our first example.